G'day, this is the second video of the angle properties of a circle. So I'll go through theorem 2 in this video here. I guess the first thing I want to just clarify or remind you of is the idea of a segment. If I've got a line here that chops through the circle, I've got two parts of the circle, and these parts are called segments. This is a minor segment and this is a major segment. I'm just going to go through the proof of the theorem 2, and then I'll show you what it is a little bit later. Imagine I've got this circle here, and I've got this chord from A to B. So I've got two segments. I've got the segment up here, and I've got the segment below down here. I'm going to look at the segment above. Now I'm going to just choose two random other points. This point over here, and this point over here. And I'm going to connect the two lines there. I've also got this center of the circle here. Now what I'm going to do is I'm just going to play around with these angles just to, I guess, show you the proof. So I'm going to just jump over to this angle over here, or this diagram. So I'm going to draw a line from A to the center of the circle and then out to B. And I'm also going to leave the line there. I know from theorem 1 that this in here is actually going to be double this one out there. That's the proof that we just looked at. Then I'm also going to look at this one over here, and we actually have the same thing going on. It looks a little bit different over there, but I've got A and B here, and I've got the angle, this angle over here subtends A and B, like on that side. So therefore, because of the rule that we just covered, if this is the center of the circle, if this one's X, this one here has to be 2x. It's a bit harder to see, but that's exactly the rule, and I guess we can prove it by measuring it and sort of working it out that way. But I guess we're left with this situation where that's x, this is 2x, and that's y, that's 2y. What we can actually see is that these angles here are exactly the same. 2x and 2y are exactly the same thing. So in this situation here, we're actually going to say if 2x equals 2y, then x has to equal y. And that leaves us with this proof. The angle in the same segment of a circle are equal. These two angles here, connected by the circumference, these two angles here will be exactly the same. X will equal y. And I guess conversely, this one here will be this angle here. Okay, that's theorem 2. I'll jump down to theorem 3, which is very similar to theorem 1, but it's just a unique case. Imagine if I've got this situation here, where I know this line here is a straight line. In fact, it's the diameter that goes through the origin. Through the center of the circle. I don't know where origin came from. So it goes from A to B, through the center of the circle, and then it connects up with this point over here, C. Now, based on theorem 1 again, I know that this angle in here must be 180 degrees, and so then when I'm looking at what this angle in here must be, I've got this line that goes from A to B, this chord, and I've got angle C subtending A and B. So therefore, based on theorem 1 again, this one here must be exactly half of 180, or in our case 90 degrees. Okay, that must be a right angle there. So the third proof is actually an angle subtended by a diameter at the circumference is equal to a right angle. So this one in here is always going to be a right angle if it goes through the center of the circle. We'll do the last and final proof down here. This is theorem 4. Imagine I have again a circle, and this time I've got a four-sided shape, a quadrilateral inside the circle, A, B, C and D. What I'm going to do is I'm going to draw the same diagram here, but this time I'm going to have the center of the circle also labeled as well, and so these two lines are connecting to there. I'm now going to label each of these angles. I'll call this one W, X, Y and Z. Okay. Now based on theorem 1 that we looked at, if I just look at this shape just here, okay, I've got I know that angle Z is half of angle X, okay, because angle X is twice angle Z. And I also know that angle W is actually half of angle y, again just based on theorem 1, this one is going to be half of this one over here. What I also know is that x plus y must equal 360. Okay, and now I'm going to just sort of crunch these things in together and find out what x and w are. So if z plus a half x, sorry, z equals a half x and w equals a half y, then a half x plus a half y must equal 180. Yeah, just divide everything by 2. So that means that z, which is the same as half x, and w, which is the same as half y, must equal 180. And this is the fourth proof that we're going to look at. So the opposite angles of a quadrilateral inscribed in a circle sum to 180. That one plus that one must equal 180. So as in w plus z must equal 180. Another way of putting that is that they are supplementary angles. And that will be true for this angle over here, where D is, and this angle over here, where B is. So those two there will add up to 180 as well. So thanks very much. I hope that has made things clear and that you're able to do some work now.